These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. So next let's talk about multiple lenses or multiple mirrors. So if you have multiple lenses or mirrors, so you would have first so I suppose this would be your first set of variables. And then when you analyzed the next device, you'd have to start using subscripts. So now you could use these numbers, these symbols for the next set of variables. So one technique here is be careful to now put in subscripts. Although, maybe, actually, why don't we just call these 1, 1, 1, 1, 1, 1, and call these 2. That feels more natural in this problem. So how would you interpret this symbol in words?
The first focal length.
So it's the focal length of the first device. And how would you interpret this in words?
The distance of the first object to the first device.
Yeah, so the distance between the object and the first device. And how would you interpret this?
The distance between the image of the first device.
Between the first device and its image.
Yeah.
Good. And the image from the first device. And then what would be our equation, our magnification equations? M1 equals?
H prime over H. Or
H1 prime over H1.
Equals negative S1 prime over S1.
Now, how will you find the object for the second device? Where will the object for the second device be?
Where the image of the first device is.
So that's one of our key ideas, yes. The object for the second device is in the location of the image for the first device. So you find the image from the first device, and then you treat it as the object for the second device. It's not a real object anymore, but you treat it as if it was the object for this device. Okay, good. So what would the magnification equations here be?
H prime. H2 prime over H2 equals negative S2 prime over S2.
Now, another concept that you now might be tested on is the overall magnification. This tells you how much the first device is magnifying, and this tells us how much the second device is magnifying. They might ask you what the overall magnification is overall, and there's two different ways to think about that. One way is what do you think should be? Is this right? No, wait. I don't think that's right. That's not right. What do you think should go on the bottom here?
H2.
Now, that would only
H1.
H1 object or H1 image?
H1 image.
That wouldn't really tell you the overall magnification, would it? The overall magnification is...
Okay, sorry. H1 objects.
So if you think about it, this is the logical way to define the overall magnification. You want to compare the original object before any devices with the final image. I don't think you can really use the S's anymore now to find this directly. But there is something else you can do. Do you know, if you know M1 and M2, do you know how to find M total?
Multiply.
That's right, so that's a good shortcut. The overall magnification is the product of the individual magnifications. Good. So it's possible you could even have a third device. Now that we have 3 devices, how would you calculate the overall magnification?
H3 prime over H1. I mean, yeah,
H1 or H1 prime?
H1.
Good, because this is the ultimate output and this is the input.
Mm-hmm.
What's the other way to find the total magnification?
M1 times M2 times M3.
That's right. Okay, good. So these are 2 ways we could find that overall magnification. This is problem 2.
So a 2 centimeters tall object facing left of a convex lens. So, okay, so 1. But if it's concave, can it have a negative focal length?
Let me let you think about that a little bit more before I help you.
Okay. Maybe. I'm just gonna put that here. So this is F2. Did I do something wrong? I'm a little confused because it's concave lens, but if the object is on the focal length, then its image is infinity. So maybe the focal point is.
Okay, I'll give you some help.
Okay.
But do you remember that problem that we did today about what was the smallest positive y?
Yeah.
But remember that you read it as the smallest possible y?
Oh my gosh, did I misread something? Did I misread something? A convex lens, concave. Oh, concave lens. Okay.
I know it's hard to
That's
draw
good
with that
enough.
maybe. All right, what matters is the center line for the thing. It'd probably be easier to draw it with a pencil. Okay, so anyway, I didn't want to just give you the answer there. So you saw something was going wrong.
Yeah.
So this is the same thing that happened on that homework problem. So just as a general rule, if something is not making sense in a problem, what's something that you should always do?
Reread it.
Reread it more carefully. That's right. Unfortunately, most people never really read the problem at all. They just kind of skim the problem. So if something, that's why I didn't want to just give you the answer up front, because that's something you could have answered for yourself. You just need to go back and read more carefully. So the problem is you were assuming it was a mirror, even though it was a lens. Okay.
Yeah. That sucks. Okay. Okay. So it's -4. Okay, that makes more sense. Okay. So. Okay. And a convex is placed AC on your start at second lens. So then this is for convex mirror. Okay. Oops. So this is so then S3 is 2 plus 8 is 10 centimeters. So then M total, 8 1/3 times 1/2 times 82, which is -1/3. And this is, oops. Which makes sense, kind of, or it should. Okay, I'm done.
What did you mean when you said it made sense?
I mean, yeah, because it's going to be negative because like it started out this way and ended up this way. And I guess this looks like it's 1/3 of that. I don't know. I probably drew it wrong.
It's not, that's, yeah, it looks not real like 1/3, but that you couldn't really expect that without drawing the scale. At least it's pointing in the right direction. That's the most that we can hope for. Okay, so let's see, let's talk about this. So it's a hard problem, but I think this would be a fair problem on the test. So one thing you did that was very good here is you were very careful with all the subscripts to use the exact right symbols. So that's important for this type of problem. And you set up a nice picture here. I noticed you had some trouble with the ray diagram here. So it's good that you just kept working at it until you figured it out. So what went wrong was, at first, it didn't seem like the outgoing light rays were going to converge.
Yeah.
So you traced them back. But then how did you realize that was wrong? Well, we know that this has to be a real image. How do we know it has to be a real image from what you figured out?
My S prime 1 is positive.
That's right, because this is positive.
And then I also looked at the chart.
Yeah, so, all right, so maybe you use the chart to figure it out, but you could also have looked at this. When this came out positive, you know that we're going to form a real image, not a virtual one. All right, and that's important. So what happened here was the only reason these weren't converging is just because we're not using a straight edge. So the angles are not really realistic here. So in order to decide whether you need the tracebacks or not, I guess the lesson is don't actually rely on your picture to figure out whether you're going to need the tracebacks or not, because we're not good enough drawers. Use the chart or use your math to predict ahead of time whether you're going to need the tracebacks or not, because we're not using a straight edge, so our angles might not be realistic anyway. Okay, so you did correct yourself there. Yeah, so one thing you might not have realized, remember, is that S prime tells you whether you have a real or a virtual image. Okay. So when you have a virtual image, how is that translated into math? How is a virtual image translated into math?
Negative.
Negative for who?
S prime.
That's right. And how do you translate a real image into math?
Positive S prime.
That's right. So when we see this, we should say that's a real image. Okay. Something that you did was really good here was that you showed that this was both the location of S1 prime and S2. That's a very good notation. But you also realized, even though they're referring to the same location, they're not the same number. So that's good. They're in the same point, but S2, S1 prime is this 12 centimeters, and S2 is this 4 centimeters. So that shows a good understanding of how to deal with this. It's probably a little bit better to use the standard notation for objects. So light rays are single lines, and objects are drawn like this. So the TA might prefer it if you draw the objects like this as a double arrow instead of a single arrow. Okay. Or maybe they won't be as picky as me. So then we had this. Remember, we had some trouble here. You drew this as a mirror, but you knew it wasn't right because it wasn't matching the focal length. So the lesson is, what should you do if things aren't making sense? Reread the problem. That's right. Okay. Also, by the way, I know it's hard to draw, but when you're drawing this lens, we don't want the light rays to be turning here. We want them to be turning at the midpoint. That tends to make the pictures come out better. That was hard to draw here because our lens turned out to be so thin.
Yeah.
Okay. All right. So then you worked through that. Looks like you left out a subscript on this M.
Yeah.
What?
2.
Yeah. So that's something that we should be careful with. Now, this M came out positive. What does a positive M mean?
It means that the object or the image is going to be in the same orientation as the object.
Which is what we usually call upright.
Yeah.
But as you were mentioning, maybe it's better just to say same orientation. So is this really an upright? Well, it is in the sense that it's oriented the same as this. So maybe upright's not the best word. Like you said, they're the same orientation. Since this is down, this is down. So that was a good thing to check. And this really did come out to be shrunk, as we were predicting from here as well. Okay, so, and then you figured out the heights here. So then we really did have a mirror here at this point. I think you drew that ray diagram correctly. And then you found M total here. So what's the alternative way to calculate M total, to double check yourself?
H3 prime over H1.
Let's adjust that and see if we get the right answer. Since we've done so much work, it would be very easy for us to have made a mistake somewhere along the way. So this is a way to double check ourselves.
So divided by 2 becomes 1/2. So yeah, this
And you got the same answer. And you can, and as you were noticing, the negative sign means that now it's opposite orientation, not opposite orientation to this picture, but opposite orientation to where we started. So notice the difference between M total and M3. M total was negative and M3 was positive, because this image is in the same orientation as the object for the third device, but it's in the opposite orientation to the original object. So those are all good things to check. Okay. All right, I think that was pretty good work then. That was a hard question, so that was a good systematic approach to that. The only problem was when you were misreading the question. One thing that you did good here was labeling all the distances. So that's very important to label all the distances so that your picture is coming out right. It probably would have been a good idea to label this distance. I think that was 2 centimeters. So that's why you said that this distance over here was 10.
Yeah.
But it's best to put that into the picture. That way you're less likely to make mistakes. Okay, now backing up a little bit here. So this was the location of the image from the first device, and then here was the second device. But what if I had said the second device was here? Then here would be the second device, and here would be its object. Do you know, how would you handle that? Isn't this kind of weird, because now the object is kind of on the wrong side of the device, if you see what I'm saying?
So it'd be negative?
What would be negative?
The object distance.
Okay, good. I don't think it's very likely that would be tested, but just in case, I wanted to briefly mention that. So remember, all this time up to now, we've always been saying the object distance is always positive, but this is the one exception to that. If you're doing multiple lenses and mirrors, and the object for one of the devices ends up on the weird side, so to speak, then you need to use a negative object distance.
Can we go over just like drawing the Venn diagram for that? Because we did that today, and like he said something weird. So I just kind of.
Okay, I'd be pretty surprised if they tested that, but I can try to show you what it
Yeah,
looks
because
like.
he was like, oh well, technically it can't go through because something's in the way, so it's like I don't know if it makes sense.
Right. Oh, before I forget. Why did you draw this as a dashed line?
Oh, I probably shouldn't have, huh?
So it's really just outgoing light. Remember, this is a lens, not a mirror. So the light should just be going right on through. You might have drawn it as dashed just because you didn't care about it. You didn't need it to find the location of the image, but it's still the outgoing light, so it should still be drawn like that. And here would be good to put an arrow to show this is the outgoing light from the mirror. Okay.
But if what I asked is like gonna take too much time, we can just go over something else and like assume that he won't test me on it.
So let's say, as in all of our examples, that the light is moving from left to right. To keep things simple, I'm just going to focus here on, let's say this is the second device, and we've already figured out that this is the image from the first device.
Okay.
So is this located in the natural or the weird position for this device?
Weird.
Weird. So the object distance would be negative. Let's see if I can figure out how to draw the ray drawing diagram. So first we're going to have the P ray, right?
Yes.
Now remember that the incoming P ray is supposed to be parallel to the axis. And where's the incoming light, on the left or the right? Where's the incoming light?
Left.
Because we know for sure it's on the left because this is where the light is coming from. Normally the incoming light ray then goes through the object parallel to the axis,
Yeah.
right? Here, it can't go through the object.
Yeah.
So we need its trace forward to go through the object. So this tells us where to draw the incoming P ray.
Okay.
So instead of using a trace back, now we need a trace forward. Normally the incoming P ray would go through the top of the object, but that's impossible here, so we need to use its trace forward to go through the top of the object. But the P ray itself is still going through, is still parallel to this line here, okay? And then where will the outgoing P ray go?
Through the focal?
Yeah, wherever the heck that is. So let's say this is the focal length. So no trouble with the outgoing P ray. All right, now we need an incoming M ray. Now, normally the incoming M ray, of course it's going to the center, but normally it would go through the top of the object.
Right.
But here, it can't go through the top of the object because the object's on the wrong side. So I think what we need is that the trace forward for the M ray should be going through. So if this is the trace forward, I would say that the incoming M ray would look like this. This is pretty weird because this is the first time that we've had incoming light from two different sides of the principal axis. But I think this is necessary in order to get it to be going through the top of the object here. So normally the M ray would go through the top of the object and through the middle of the lens. Well, now it's impossible for the incoming ray to go through the top of the object, so its trace forward goes through the top of the object. And then where should the outgoing M ray be?
It just goes straight through?
It's the same as always. Incoming is just a straight line, so that'll obliterate this dashed line here. And now where's the image?
Where the things coincide?
Right here. So I should have drawn my lens as narrower because it's interfering. So then it would end up like this. So this would be the image from this device if you have to draw the ray diagram.
Okay. And then if it was sorry, I'm not getting my, okay, so that's a converging lens. So if it was a diverging lens, then,
Can I erase this?
yeah,
Yeah.
can we just quickly do that one, that example also?
So here's the second device. Here's the first image and the second object. So the incoming P ray normally would go parallel to the axis through the top of the object. Here that's impossible, so it's the trace forward. So it doesn't seem much different here. That goes through the and then where should the outgoing P ray go?
Through the focal, but it's,
Focal point on the left or the focal point on the right?
on the left?
That's the way this type of lens always works.
Yeah.
For this type of lens, you would always use this side. Because remember, it makes the light rays diverge away from the principal axis.
Yeah.
So I actually should draw it. So the trace back. So far, the fact that it's diverging doesn't really affect this virtual object very much, because the fact that it's diverging only affects the outgoing light rays, and the fact that this is a weird object mainly affects the incoming light rays. That should make sense to you, because what we have here is a weird object. So that's going to make our incoming rays weird, not our outgoing rays. The outgoing rays we're just going to draw the same way we always did. The hard part is knowing how to draw the incoming rays. This is what you could call a virtual object. We've talked about virtual images before. This is like a virtual object. Remember that when you draw a real image, you use the outgoing light rays. But when you draw a virtual image, you need tracebacks. When we normally deal with a real object, we use incoming light rays. But for virtual objects, we also need the trace forwards, which is what we're doing here. All right, and then the M ray, I think it's the same exact M ray as before. It just traces forward through here. This is going to work. And then where should the outgoing M ray be?
Just straight through.
It'll just go over this line again. It's the same exact ray as before. M rays look the same for diverging and converging lenses. And where's the image?
Where the lines intersect.
Over here?
On the left.
Over here. So we would predict here that the way I've drawn it, we're going to get a inverted and maybe a shrunk image. And also it looks like we're getting a virtual image. Okay. So.
And it's virtual because one of the things is a traceback. Like even though the M
They're actually both tracebacks. Because remember, the image is where the outgoing light rays or their tracebacks converge.
Okay.
So here, clearly, we did not use this outgoing light ray. We used this traceback.
Right.
But I didn't use this outgoing light ray either.
Oh. Okay.
The only reason it looks like I didn't use the traceback is because the traceback dashed line has been covered up by the solid line for the incoming ray. But you can see we're not using the outgoing light rays because those are on the right.
Yeah.
So we are using the traceback. It's just not easy to see because it's underneath the solid line.
Okay.
That's right.
Okay. Thank you.
Okay. I think it's pretty unlikely that would be tested.
Yeah.
I think it's unlikely that they would have negative object distances at all. And if they did, they'll probably only want you to do the math
Okay.
and not require you to draw the ray diagram.
Okay.
But just in case, this is how to do it. All right. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.